Here's how to analyze the data that you got from the acid-base mole ratio lab. And this is probably the most complicated set of traces that you've ever generated with a computer-based program. But it's really quite simple if you think about it. When you put the acid into the base, the sodium hydrogen carbonate, first of all, you let it run for a while at atmospheric pressure, and that's down here towards the bottom. And that's your baseline pressure. What you want to measure is the pressure increase. And so the pressure increases. It's not linear, but it's a good increase here. And what you're looking for is the level pressure. What does it level out at? Now you can do that with the tool that's provided to you in the Analyze, Examine. And you can just come over here and see, you get kind of an average of the starting pressure, which as you can see from these boxes up here, it's about 99 in this case, 99 kilopascals. And then you come over here, and I'm looking for this first line with 1 milliliter of acid added, and I can see that we're right around, let's look up here into the box, and the box says 101.54, so you can use that. Don't get the peak, don't get one of these little troughs here, and don't wait too long, because your hand, you're probably holding the flask and your hand is warming up the gas, and it may be increasing the pressure because of that. So get one of these middle points in here, and on the second one I look at it, and right about here it says it's 102.87, and so forth, all the way on up. And you notice when you get up here past the 3, or into the 3rd, 4th, 5th, 6th, 7th, things start to level out. You don't get much of a difference between the starting pressure and this ending pressure here. There's a little bit of statistical wiggle in the numbers, but they all look very, very close to the same number. And so we're going to write down all of those final pressures for 1, 2, 3, 4, 5, 6, and 7 milliliters of acid added. Now you see I have switched to a spreadsheet program in order to do some calculations. There are a lot of ways you can do this. You can even do it by hand. But I find it's a lot easier, and my handwriting's a little poor, so you'll probably be easier to see right here. And you can see what I've done is I've written down the acetic acid for each of the 7 runs, and of course we've added the 0. And I've put this average initial pressure, atmospheric pressure, in a column here. And I've put each of the level pressures that I recorded from the 7 traces, I've put those here. So you'll remember about 101.2 for that first, and then I've got 102.8 and so forth. And then here, if you'll look, I have subtracted the final pressure minus the initial pressure, and of course here it's 0, and then it just goes up. And then as you notice, it started to level off. So these are the pressures that we're going to use. Now on the other slides I showed you how, even before the lab perhaps, how to calculate the number of millimoles given the number of milliliters of acid. We multiplied the number of milliliters of acid you added by the molarity of the acid, 0.42, and with each one of these runs, 1, 2, 3, 4, 5, 6, 7 milliliters, we had the same increase in the number of millimoles. So this is millimoles of acid, and it goes up in a straight line. And here's your carbon dioxide pressure, which does not go up in a straight line. You can then, if you wish, either graph this by hand, you can graph it with the computer here. We can graph it with this spreadsheet program. So I'm going to do that real quick for you. So we paint out all of that area where we've got what we want to graph. The millimoles of acid will be our independent variable. The carbon dioxide pressure will be our dependent variable. And we click up here, whichever one of the icons gives you a chart, a graph. And in this case, it doesn't give us a good one because we want a scatter graph. We always want a scatter graph. So we click on that, and we're just going to do the points. Finish the graph. Now you can see what's happening here. As we add more acid, and we know the acid is limiting here, as we add more acid here, we get a fairly linear increase in the amount of carbon dioxide produced. And then once we hit a certain point, it levels off. Adding more acid gives us no more carbon dioxide. I've taken these numbers for a specific set of results from, not these results, but kind of an average set of results. And I've moved them back to LagerPro, and we'll show you that here in a moment. Here are some representative numbers. This X is the millimoles of acid added, and this Y is the pressure. Now we can actually come up here, right click, and change the name on top of there, and we'll just put acid millimoles. Acid millimoles. And then we can right click on this Y and change that so it says pressure of carbon dioxide. And we'll say pressure, and the unit is kPa. And so now our graph tells us what we have. Now what can we do with this? Well, as you know, LagerPro enables us to draw straight lines. It's got a linear tool. So if we paint out these increasing points, including the 0, 0, we can click on linear fit and get a linear regression, a straight line. We then can take these level points and do the same thing. Paint them out and get a straight line. The intersection should be the point where adding more acid gives us no more carbon dioxide. And we can use the examine function here to find out what that is. And if you look down to the axis, you see it's very close to 1.5. I'll just remind you that we had 1.5 millimoles of the sodium hydrogen carbonate in the flask each time we ran this. And I suspect that when you do your numbers, you will have numbers maybe down here, could be up here, when those two intersecting lines are going to see this point where the two lines intersect. That is your ratio of the acid and base. That's the number of millimoles of the acid that was added to neutralize your base. The ideal, of course, is 1.5 because the balanced chemical equation says that 1.5 moles of the sodium hydrogen carbonate will require 1.5 moles of the acetic acid. So you can get a percent error from that simply by subtracting your number of millimoles of acid from the 1.5 that we know from the balanced chemical equation we should need, and then divide, of course, by 1.5, multiply by 100, and that gives you your percent error in this lab.